Okay, we're back one more time. Now, we've done multinomial logistic regression. We've seen a dramatic improvement in multi-layer perceptrons. So now we're going to try the convolutional neural networks. So we've made it to the latest cutting-edge deep learning technology now. All right, so let's see what we can do. I'm not sure that we can make an improvement on 97%, but maybe we can. So let's try it out. Now, there's one thing I want to call to your attention. If you remember before, this image set had been flattened, right? Every image was a flat 784 number array. So convolutional neural networks want to look at the picture in its entirety and move a patch over that picture. So I'm going to have to reshape all of my training images so that they're the correct dimension, the original dimension of the photo. We're going to use the actual photos now, not just a flat line of numbers. That's pretty cool. All right, let's look at the implementation for CoveNets. It's going to be a little bit more complicated, but I'm probably not going to explain too many of the details, but that's okay. The important thing is that you understand the high level part of this. If you ever need to do this, you'll be able to get much more into the weeds on your own. Okay, so a couple of new hyperparameters here. Patch size is going to be 5. Number of channels is 1 because I only have one channel in this case. It's grayscale image. This would be 3 if it was a color image. All right. So I've made these functions to initialize weight and bias variables because there's going to be so many of them now that it'd be kind of a pain to build them all. I've also built a function that can build convolutional layers. And so this is going to create a convolutional 2D layer for a network. And then this is going to create a max pooling layer. And the reason I do this is because I'm going to need more than one convolutional layer. I'm going to need more than one max pooling layer, and I want to stack them together. All right, this hasn't really changed that much except for here. You can see that I am reshaping my data set to be the correct size. And here I'm also reshaping my data set to be the correct size. I'm going to here expect that the image is going to be 28 by 28. So when I train, I'm going to need to feed it correctly formatted images. Getting the matrices right is probably the hardest part of most of this work. Okay. So I'm going to build 2 convolutional layers. There's going to be 2 fully max pooling layers. There's going to be 2 fully connected layers. All right, and here this is going to initialize the variables for all of them. And then this is my model. So now my model has data that comes in. It runs through a convolutional layer. It's then going to run through a max pooling layer. Then it goes through another convolutional layer. Then it goes through another max pooling layer, and then gets flattened. And then we're going to do a ReLU on the flattened with the first set of weights. So this is a fully connected layer. This is kind of like a hidden layer. Then we're going to run dropout, and then we're going to have the logit layer. This is the very last readout layer, and this is going to be what was called logit before. In fact, it's still called logits here. Okay, so what we do is we run the model on the training data set, and when we do that, it runs all of this, convolution pooling, flatten, hidden layer, readout layer, dropout. Okay, and then we're going to compute the loss function, same as before. I've removed regularization at this point because it just gets really complicated with this many layers. The optimizer then is going to run stochastic gradient descent straight on loss. And then this is exactly the same. All right. Let's hope that my video card holds out this time. So what we're going to do is we're going to generate a mini batch. We're going to reshape that mini batch. We're going to feed it to the network. And this is all the same. So let's see if convolutional networks can outperform multi-layer perceptrons. Let's see if my video card holds together. Okay, so we're at step 0 and we're waiting for step 500. You can see that the original accuracy is pretty bad, which is what we would expect because the network hasn't learned anything yet. You can also see that things take quite a bit more time here. All right, there's step 500, and look at the improvement. We're almost better than our previous example already. We're at 95.9%. Now, this is going to take a little bit of time to run. My computer has a GTX 745. It's not the greatest video card out there, and so it's not especially fast. What I'm going to do is I'm going to pause the video and I'm going to resume it at the outcome of training. Hold on. Okay, and 10 minutes later, we are back. My network has finally finished training. And I think this is interesting for you to look at too. You can see that what was happening over here on the standard out of my IPython notebook was, should be in here somewhere. Here it is. Yep, I kept getting these messages. The caller indicates that you don't have enough memory. You're trying to allocate 2.6 gig to the video card, and you can't. So yeah, I was running out of resources, and I wasn't sure that things were going to work out, but it turns out they did, and they worked out pretty well. My test accuracy overall was 99%, and that's pretty good. So how good could it be? The world record for MNIST is 99.77%. So we're not a world record holder at this point, but that's okay. With a little bit extra work and some hyperparameters, I think there could be. So how did the world record? How was the world record set? Well, they used a convolutional neural network just like this one, except they didn't use one. They used an ensemble of 34 convolutional neural networks. Just like with Dropout, more than one is always better than one. Ensembles are a way to usually improve a model. Okay, so that shows you how the convolutional neural networks can improve on the previous results. Now, these convolutional neural networks, they do really good at these trivial problems like MNIST, but they're revolutionary at real image recognition problems. And they really can do some amazing things when you care to recognize much more complex things like, is it a cat or is it a dog, or is it a broken car or a fixed car, or is there a pedestrian in the crosswalk or isn't there? And all of the self-driving car technology, all of these things revolve around what we've done with CoveNet. So they're very important. All right, so we've gone from, just to recap, multinomial logistic regression. Then we've stacked a layer on top of it and made a multi-layer perceptron. And now we've gone all the way to convolutional neural networks. Hope this was fun and hope you enjoyed it. Thanks a lot for watching.